Hello, everyone. Thank you for joining us for another live webinar hosted by ETech and All About Circuits. My name is Dale Wilson. I'm the VP of Engineering and Content, and I'll be your moderator today. Today's session, Innovative Charge Pump Capacitor Divider Technology Improves Intermediate Conversion Efficiency, is brought to you by pSemi and RFMW. Our presenters today are Tatsuya Kubo and Doug Osterhout. Kubo has been with Murata pSemi for 25 years and has contributed to the power business in design and marketing roles. He has a bachelor's degree in electrical and electronic engineering from Ritsumeikan University in Japan. Presently, Kubo is the product manager for pSemi's high-efficiency buck regulator and charge pump portfolios. Doug has been with pSemi for 3 years as a systems engineer and product definer. He has worked in various roles in the power electronics industry for over 25 years. He has a BSEE from Binghamton University in New York and is a member of Eta Kappa Nu, Tau Beta Pi, and is a senior IEEE member. Following the presentation, we'll have a live Q&A session with Kubo and Doug. You can submit your questions at any time during the webinar using the Q&A section on the right-hand side of your screen. You will find a downloadable copy of today's presentation in the Handouts tab near the end of our session. And I'll be back for our Q&A session, but now I'd like to hand things off to Kubo to begin their presentation.
Hello, everyone. Thank you for joining and welcome to pSemi RFMW webinar. My name is Tatsuya Kubo, Senior Product Marketing Manager at pSemi. I am responsible for charge pump and buck regulator product using our own unique technology. I also have Doug Osterhout, Product Definer and System Application at pSemi. First of all, a quick introduction of pSemi Power. We are now fully owned by Murata, a Japanese leading company for passive components such as MLCC, EMI component. And today's main topic, power-related product, came from acquisition we made back in 2017. We acquired power semi company named Arctic Sun, who was startup from MIT. They have many patents related to switched capacitor technique. The content we will present today is based on their technology. Today, we will introduce an innovative capacitor divider technology that enables us to improve intermediate conversion efficiency with ultra-low profile. We hope you will learn a lot about new technology behind the pSemi Power product. We also hope this webinar will give you some idea how to solve the problem that you are facing now. Here is the agenda we'd like to go through together. We will start from problem statement highlighting how much power is annoying your system design and what is a major problem for power design. And then overview of pSemi core technology and product offering. In the third part, I will hand it over to Doug to cover a deep technical session, which is today's main topics to introduce pSemi's lossless charge pump technology. So we will dive into detail of our charge pump technology, spotlighting what is the difference from traditional charge pump. What is the beauty of pSemi charge pump? After Doug's session, I will take over again and as practical implementation. We will introduce some of highlighted products using this new technology and how those parts can be implemented in the actual use case. And we'll be closing with some key takeaways. We will also have Q&A. We hope we receive many questions, and we will try to answer as many questions as possible. All right, let's get started. My first comment here is, what is the problem? We know power conversion always causes lots of headache, eating lots of space, generating heat, radiating a noise. This is one of the example motherboard of computing platform. power conversion can easily occupy 25 to 30% of circuit board. Actually, power component keeps eating as much as 55% of your real estate, especially in high-performance platforms such as GPU, AI processor. Inductor is typically the largest footprint and highest single component. Please do not forget that you may be required expensive filtering for both input and output in order to maintain power line as clean as possible. Many people have a problem with inductor. Inductor can be the biggest enemy in your system. You know what is the best way to find power conversion area on the motherboard? Just find inductors. Then you will see how much inductors are eating the space in your real estate. We are trying to solve this situation with new technology. Here is a very interesting comparison between capacitor and inductor. Actually, capacitor has potentially 400 times higher energy density than inductors. This means capacitor is no longer just for filtering, decoupling purpose, but becoming key component for power conversion. This is why we are proudly introducing a charge pump, trying to change whole power industry with this new technology. pSemi core technology and power product family. Charge pump is our core technology. You can think of it as a virtually lossless DC transformer enabling very small and ultra-low profile solution by using capacitor. This is open loop topology, which means a Vout just tracks a Vin. Vout is fixed ratio of Vin. We can do divider or multiplier by certain ratio. For example, if you apply divider for charge pump to 48 input voltage, you will get 12 voltage as output voltage. 48 to 12 is very popular voltage conversion as an intermediate bus architecture in data center, networking application. We can do several divider ratio in one part, such as divider 2 and 3 in one part. But efficiency stays almost same regardless of divider ratio. We have a phase interleave and soft switching technique for low ripple and EMI performance. And inherently parallelable, very handy and scalable solution as this is open loop topology. Here are product offerings from pSemi power product family. Starting from the left, charge pump, switched capacitor converter. Again, this is our core product, virtually lossless, incredible high power density. Both discrete and module solutions are available. Suitable for multi-cell battery platforms such as laptop, DSLR camera, drone, VR. Also 48 bus systems such as data center, ATE, and robotics. Second product is two-stage buck regulator, which means charge pump followed by low voltage buck regulator. While VR of charge pump is unregulated, this two-stage buck provides regulated voltage. We divide input voltage by certain ratio to go with lower voltage FETs and much smaller inductor in downstream bucks. Very high efficiency with ultra-low profile. This is very nice solution, especially for height-constrained applications such as optical transceiver, PCIe, and memory card. And third product is also two-stage architecture, but reverse direction, which means boost converter for powering up a LED backlight. tiny size, ultra low profile below 1 millimeter with highest efficiency in the industry. Any low profile panel display, such as laptop, tablet, mobile, and handheld gaming with LCD display, must be willing to bet this product for better battery life. And the last product is multi-level back regulator, which is fresh arrival to our product portfolio. Recently, we have released industry-first 4-level converter in the market. High-efficiency battery charging with 1 mm height solution, aiming for one-cell battery charging from USB PD or PPT input inside of smartphone and tablet. As you can see, we have 4 product portfolio. All of them are based on capacitive switching architecture, targeting for low profile, space constraint, and high efficiency application. And today, we will focus on charge pump switching capacitor products, as this is a key differentiation point from what other competitors are doing. Okay, now everyone may have a question. What is pSemi battery lossless charge pump? What is the difference from other solutions? How this solves the problem? You will see the answer from now. Let's dig into the detail of a charge pump technology. I'll hand it over to Mr. Doug.
Thank you, Kubo. So let's look at enabling more efficient power conversion with pSemi's lossless charge pump. So power loss in a standard charge pump, if we take a look at a simple divide by 2 charge pump. So there's 2 basic states in a charge pump. The fly capacitor here is getting charged. It's connected between the input voltage and the output voltage. So current's going into the fly capacitor, charging it up, and delivered to the output. And then the second stage is the fly capacitor now is getting discharged, and current in the fly capacitor is being discharged, delivered to the output. So similar to a buck converter, where a buck converter has 2 stages as well, or 2 states. So in steady state. But there's a transition that happens, and during the transition, there's no inductor that's forcing current during the transition. So the load current is supplied by Cout, and no current path is established until the switch nodes have transitioned. So as we switch, so first the fly capacitor is connected between the input and the output voltage with these 2 FETs on. And then next, as we transition, one of the FETs turns off, and the fly capacitor is still connected. One end of the fly capacitor is connected to the output voltage. Now we switch where the end of the fly capacitor is connected. And then we connect the fly capacitor to the output voltage. So now the fly capacitor is in parallel with the output voltage. Then we have to switch the fly capacitor again so that eventually it's connected to the input voltage in the opposite direction. And now it's in series. The fly capacitor is in series between the input and the output, and the fly capacitor now is charging up during this state. So, excuse me, if we look at the losses, there's no commutation losses. So if you're familiar with a buck converter, you're probably familiar with the gate drive losses, the I2C losses. You're probably not familiar with charge redistribution losses. This is something unique in a charge pump. We'll talk about that in a minute. But if you're also familiar with buck converters, you probably know about the switching losses. And switching losses can be dominant in a buck converter, and they increase rapidly with input voltage. Charge pump, we don't have the switching losses in the same way we do with a buck converter. So on the right is a table. During each of the switching transitions, there's one loss that dominates. Either the I2R loss, which is the conduction losses through the channel of the MOSFET, or the gate drive losses. As we charge up the MOSFET gate, we have energy going into the gate. And as we discharge the gate, we discharge the energy into ground. And we lose that energy when we're switching the MOSFET for the gate drive losses. And there's two states, state number 2 and state number 4. We have this thing called charge redistribution losses, so we'll talk about that in a minute. So the charge pump losses, what happens if Vn is increased? So for a comparison of a charge pump versus a buck, if we assume that the net I squared R losses are the same, this charge pump architecture used by pSemi is a version of the divide by N. Below is a simplified version. So all switches see a maximum of 2 times the output voltage. And you see all these different stages are in parallel connected to the output. So in this topology, as Vn increases for the same output current with the same voltage and die area, the number of stages increases linearly as we step up in input voltage. So the voltage rating of each state remains constant. Remember, it's only 2 times the output voltage. The current through each stage reduces linearly because remember the stages are put in parallel, so we add more stages with increase in voltage. So the impedance of each stage increases linearly as well. So the gate drive losses actually stay constant when we increase the input voltage. And the I squared R losses stay constant as we increase. So all losses stay constant as we increase losses. So if you're familiar with buck converters, power loss increases fairly rapidly when we increase input voltage for a buck converter. Buck converters don't work very well when the input voltage and the output voltage are very far apart. So if there's a high input voltage, you'll have a lot higher loss in a buck converter. But you won't see that with our charge pump. So what's different about our charge pump? So in pSemi's charge pump, all the switches are exposed to a maximum of 2 times V out. And the burden of withstanding high voltages is on the capacitors, not the switches. So the switches can all be a lower voltage. And the gate drive losses stay constant with Vn. This pipeline architecture parallel paths for current to the output. On the bottom is a traditional series parallel charge pump. So here the switches are exposed to Vn and V out, and they scale with Vn. So at higher voltages, the higher switches see higher voltage. The bottom switches exposed to V out and ground, and they don't scale with Vn. But all the other switches, as they move up the ladder, get higher and higher voltage. So all the other stages are somewhere in between. And lastly, the gate drive losses increase with Vn since the gate capacitance increases with the voltage rating. So in pSemi's charge pump topology, this charge pump pipeline, each capacitor moves the charge down 1 step. So we always charge a capacitor to V out, creating a current multiplication effect as we step down the voltages. So what about charge redistribution losses? So you might not be aware of this if you've been working with normal buck converters and other types of converters. But if you take 2 capacitors and you connect them together, in this example we have one capacitor charged with 1 volt and one capacitor charged with 0 volts. You might have seen this example before. When you do this and you connect 2 capacitors in parallel, you lose half of the energy. And so this is a very common thing. So half the energy is lost. So this is the worst case when one capacitor is fully charged and one capacitor is charged at 0. If the capacitors are the same voltage and you connect them in parallel, you lose no energy. If the capacitors are slightly different, you'll lose less energy. But you always lose some energy if there's a voltage difference on capacitors. And this is how charge pumps work. They connect capacitors in series or parallel. So you lose some energy through redistribution losses. But on the right, we have something called this adiabatic charge pump. So adiabatic, by that we mean no power loss or no energy loss. So if you connect a capacitor in series with another capacitor, but this time put some inductance in series, it dramatically cuts down the redistribution losses. If there's no resistance, you won't have any, ideally, and the energy will just cycle back and forth like an LC circuit. So the second drawing, though, is we're connecting this in series with a buck. So in that case, the buck actually draws a constant input current during the switching cycle. So while the buck feds on, it's drawing basically a constant current on the input. And so we use that with our charge pump to draw a constant current out of it as we switch the capacitors. So we use this current source to keep the current constant. So this current basically emulates an inductor via the buck stage. And so this charge redistribution is stored in the inductor and is recycled to the output losslessly. So this lossless adiabatic charge pump, here's an example where we have a charge pump in series with a buck converter. So in this case, it's a 3-to-1 charge pump. So when the buck fed is on, we're pulling a current, charging on the left side, we're charging the charge pump capacitors in series through this constant current through the high side FET. And then the second stage, when the fly capacitors discharge, they're still connected in series with the buck, and the buck FET is still on, and they're pulling a constant current now out of the capacitors as the fly capacitors are discharging. So here, the fly capacitors are charging, and the second stage, the fly capacitors are discharging. So the buck resembles a current source on a cycle-by-cycle basis. So the buck is synchronized and in series with the charge pump. So during both phases of operation, it eliminates all the charge redistribution losses. The inductor controls the charge between the capacitors. So all the voltage differences between the capacitors are dropped across the inductor. And the inductor effectively recycles the energy in the inductor to the output. So this is basically a method to doing a lossless charge pump. So it nearly eliminates all the capacitor charge redistribution losses, and it makes the charge pump a practical transformational element. So summary of the benefits. So in combination with either a buck stage or a boost stage, the pSemi charge pump is virtually lossless. We get very high efficiency. The losses are virtually independent of Vin, so we're very good with high conversion ratios, with a high input voltage and low output voltage, or a big difference between input and output voltage. The entire powertrain is also able to use low voltage switches. So because our topology uses MOSFETs that are only rated at twice the output voltage, we can use a low voltage process. Next, the charge pump size is constant and no longer dependent on the I²C. So if we increase the input, we increase the number of charge pump stages, so it's more parallel path to output, and the increase in number of charge pump stages is directly proportional to the reduction in current. On the right column, the switching losses are dramatically reduced and no longer related to Vn, so this enables higher switching frequencies and overall higher conversion efficiency with vastly superior light load efficiency. Converters generally have poorer performance and poorer efficiency with higher input voltages or a larger difference between Vout and Vin. So if Vin is very high and Vout is very low, buck converters are not as efficient. The burden of the energy storage now, as Kubo mentioned before, is in the capacitors, not in the inductors. So the capacitors can store much more energy than the inductors per unit area. Also, generally a buck inductor needs a larger inductor if there's a large difference between input and output voltage. So we can reduce that difference by using a charge pump in front. So the buck inductor can also be smaller. The last point is this pipeline architecture means small voltage steps throughout the powertrain. So this reduces inrush current, which significantly lowers input current ripple, which should lower EMI. Okay, thank you. Now I'm going to pass it back to Kubo for practical implementation.
Thank you, Doug. This is Kubo again, and let's move to the next session. As practical implementation, we would like to highlight some products based on this technology and how these parts can fit into actual environment and how we solve the problem. Early this presentation, we presented 4 product portfolio: charge pump, 2-stage buck, LED boost, and multi-level converter. In this webinar, we just focus on charge pump product. We have both integrated module solution and discrete solution. Key benefit of charge pump is high efficiency with small footprint and low profile. In the table from the left, of 48 bus architecture, we have PE25304 as a div4 charge pump module and PE25208 as divider to charge pump discrete IC. For low voltage applications such as 2-cell, 3-cell, and 12 voltage point of load application, we have P25200, P25203, and P25213 as discrete solution with selectable divider ratio between 2 and 3. And specifically for USB PD EPR application, P25208 can also play around with either Div2 or Div3 mode to enable fast charging mode through existing charger platform. So we are offering several choice of divider ratio depending on input voltage, battery configuration, and power range as per system requirement. And today on this webinar, we will highlight PE25304 and PE25208 for high voltage 48 bus architecture. First product is PE25304. PE25304 is charge pump module solution aiming for 48 bus architecture. All flying caps and inductor are integrated in one package. Only few filtering caps are required. Wide input range from 20 to 60 voltage. Divider ratio is 4. This means a Vout is always 1/4 of input voltage. One part can support up to 6 amp and can be paralleled up to 4 to support over 200 wattage range. With operating temperature from -40 to 105 degrees C. Very tiny LGA package 11.5 by 9.5 by 2 mm height. Incredible high power density 5.4 kilowatts per inch cube. And very high efficiency 97% peak efficiency with ultra low profile. And excellent thermal performance and low input and output ripple. This is a basic performance comparison against traditional solution. Those are 16 brick, which has been used as intermediate bus converter from 48 to 12 in many years. Our solution size is 80% smaller and height is 75% lower. Generally speaking, if you go smaller and thinner solution, you have to sacrifice efficiency because you have to shrink inductor size. But not for us, because we are using capacitor for voltage conversion with less dependency on inductors. So even with smaller and thinner solution, efficiency is way better for entire load condition. And this reflects the thermal performance. As you can see, our temperature rise is 50 degrees C lower. And better ripple and EMI performance that are brought by our interleaf charge pump architecture. And lastly, what we want to emphasize here is weight comparison. P25304 can give you 95% weight saving, which is incredible, and highly beneficial for the applications such as humanoid robotics inherently exposed to shock and vibration all the time. Today, we'd like to highlight one more product, which is PE25208. P25304 we presented in previous slide was module solution. On the other hand, this PE25208 is discrete solution. As you can see layered photo, in this case, we need flying caps to be populated on customer board. However, all FETs and controller are still integrated in monolithic die. So PE25208 is fully integrated charge pump IC. This part has selectable divider ratio. So you have a choice of divider ratio between 2 and 3, depending on input and output range stated under a layout portal. Very high efficiency, 98% peak efficiency with small footprint. Wide input coverage enabled to support not only for the 48 bus, but also for 24 bus architecture. And better light load efficiency with a pulse skipping mode, which is essential for battery application. Here are some implementation examples with PE25208 and PE25304. PE25208 can play around battery applications such as laptop, drone, and power tool. On left-hand side diagram, fast charging is required from high input voltage such as 48. PE25208 with DIV3 mode can provide lower input voltage to go with existing charger circuit. So PE25208 can enable very simple implementation of fast charging to improve charging time. And also for discharging area. As an example, for 4-cell battery application, PE25208 with DIV2 mode can convert to 2-cell voltage, which help improving efficiency by using low voltage FET in downstream regulators. More efficient way lead to longer battery life. On the right-hand side is for 48V or 24V industrial application, such as semiconductor manufacturing, robotics, and ATE. P25304 with DIV4 mode can convert from 48 voltage to 12 voltage, which is very popular intermediate bus conversion widely used for many applications. And then you can go with 12 voltage input general point of load solution from broad market product. P25208 can support 24 bus with DIV2 mode from 24 voltage to 12 voltage. Same scenario as P25304 for 48 voltage. You can get 12 voltage as intermediate bus voltage. So we can offer a choice between divider for charge pump or divider to charge pump to get common 12 voltage bus voltage from either 48 voltage or 24 voltage. Again, the value proposition of our charge pump is very high efficiency with low profile, enabling to save power consumption, as well as to go backside of PCB for free up more space on the top side. Here is a more specific example, which is for humanoid robotics, particularly a dexterous hand. In order to reduce iSCAR loss on the cable from a battery pack, you want to bring 48 voltage as close to the edge as possible. And then you need a local voltage conversion from 48 inside of this hand. However, there is a big hesitation to use inductor due to not only space and height restriction, but also concern about the shock and vibration because robotics is moving all the time. And of course, no one wants to lose efficiency because this is powered by battery. Our charge pump can eliminate those concerns because this is capacitor-based topology, less dependency on inductors, but very high efficiency. Let's just put P25304 here and you will get 12 voltage for powering up finger motors and downstream bucks. If you need different voltage, such as a 24 voltage instead of 12 voltage, P2528 can be the best choice for you. More efficient for longer battery life. Smaller footprint and lower profile makes overall system much lighter and much robust over shock and vibration. Alright, today we presented the detail of charge pump technology and product offering. We picked two specific products as implementation example for humanoid application. And we'd like to close this webinar with 3 key takeaways. P25304 and PE25208 are the very high power density intermediate bus converters priced where space and height are constrained. Capacitor-based topology allows drastically reduced inductor size for lightweights in the entire design. Ultra-low profile and lightweight solution is highly beneficial for robotics application inherently exposed to shock and vibration. Thank you for joining our webinar today. I hope the content we presented today were valuable for everybody. Hopefully, you could come up with some idea how to solve your problem by using our charge pump technology. We will keep evolving this technology and trying to change power industry. We are looking forward to future business with you. Thank you, and now we can move to Q&A session.
All right. Well, thank you, Kubo and Doug, for that really fascinating introduction to this new technology. I love the bold objective to change the entire power electronics industry. And I also find it interesting how you've taken some concepts that have been relatively common in the low power semiconductor industry, like switch capacitors and adiabatic logic, and then you've co-opted them to solve these challenges in the power electronics world. So really good stuff. We already have several interesting questions in our queue, but I will remind everyone in the audience, there's still time to submit your questions. Just type those into the Q&A section on your screen. So with that behind us, Doug, Kubo, you guys ready to answer some questions?
Sure.
All right. Sure. Excellent, guys. All right. So the first one here is asking, in the phase 2 discharge stage, the capacitors are turned off. Is that right?
I'm sorry, I don't remember what the phase 2 stage was, but generally with the fly capacitors, well, not generally, you have to have charge balance. So in one state, the capacitors are charged, and in the next state, the capacitors are discharged. So there's usually 2 different states. So you have to make sure the capacitor is balanced, the charge is balanced. During the transition time, you have to make sure there's no shoot through and other things. So when it transitions, there's some time, very short amount of time where you switch, where you have to remove the capacitor from one to another before you connect it. So you can't just directly switch from charging to discharging. You have to take a little bit of time to turn off FETs and switch over to the next FETs and make sure the FETs are off so there's no shoot through or crazy things that happen. I hope that answers your question.
Yeah, and if it didn't, they can submit another one. We still have time to get to it, so we'll keep an eye out for that. So, all right, great. So this one's asking for a little clarification. Just, are all the capacitors involved in the switching, are they inside the modules?
No. So we have a power IC, like a controller or a converter, which has the power MOSFETs and the silicon and the control circuit and all that stuff inside. And then like a normal, maybe power, like similar to like a buck IC. And then the capacitors are all external. The capacitors are probably a little too big to put on silicon. Mm-hmm. In a module, that's possible. But these aren't modules. This is just silicon.
Got it. And I guess I think I'm going to follow up a question on that is, are there specific types of capacitors or key capacitor specifications that you need to select your capacitors for?
I think not so much. I mean, the normal X5R, X7R, or whatever you want to use is okay. Generally, they're in the tens of microfarads, ceramic caps, so just ceramic caps, and Most ceramic caps are very similar. So I don't think there's nothing special about it. Just normal ceramic capacitors.
Got it. Yeah. Nice and easy. Okay. This person is asking, do the PE25304 and 2528 have isolation?
I can answer. The answer is no. All of our charge pumps have no isolation. So if your system requires isolation for some safety reason, please make sure you have isolation device such as AC/DC or the transformer-based DC-DC converter in front of charge pump.
Okay. This question, I'm not sure I'm following it, but maybe you gentlemen can. If a multi-capacitor is clustered, not, I don't know what that next word is, not divided, but yeah, I can't parse that question.
I'm sorry, I don't quite understand either.
Okay. We'll archive that one and take a look at it, but and maybe get back to it, or you can follow up after the event with pSemi and they'll try to help you with that. All right, another question. They're coming in fast and furious. That's awesome. Will the divider ratio be affected by the capacitor drift over temperature?
This is a really great question. No. So really quickly, no. So the output voltage, these are generally non-regulated. We do have some regulation stuff that we didn't mention here as much. I think Kubo mentioned a little bit, like multi-level buck converters, which are pretty interesting and pretty fun. But the capacitor drift won't affect that. But there is a problem. I mentioned the charge redistribution, that when you charge two capacitors together and the capacitance is different, like if the voltage is different, so if one's at 0 volts and one's at 1 volt, and you put them together, you lose half the energy. And if the capacitor voltage is smaller, if they're the same voltage, you lose 0 energy. And if the voltage difference is in the middle, then you lose about some percentage of the energy every time you switch. That's a normal charge pump. Our charge pump, one of our big IP things is we, like with the buck converter one that I showed, where we pulled the constant current because of the buck input current, or we put a very small bead inductor to add a little bit of inductance to kind of resonate, and we take care of the charge redistribution. So in a charge pump, if you want high efficiency, for other charge pumps, you have to use really large capacitors so the voltage doesn't drop as much. Our charge pumps, you can get away with using much smaller capacitors because we'll use this resonant thing with the inductor. So as the inductor, we'll use this resonant thing with the inductor. So as the capacitance, so we can get by with this much smaller capacitance. This is a really complicated question, or maybe more complicated answer, but of course, though, the capacitance drops with DC bias quite a bit with ceramic capacitors and other things. But the good thing about our topology is you can get away with smaller capacitances and still get high efficiency. So the drift doesn't affect. The only thing that affects the output voltage drooping down is really the RDS on of the MOSFETs.
All right, thank you. Next question. How tightly matched do the flying capacitors need to be for the discrete implementation?
That's not critical. It's not really critical. So, and we've tried on the bench too, by the way, mismatching them and doing other strange things to see if you get better efficiency, if the high sides are bigger or smaller. It's not critical at all that they be matched.
Oh, fascinating. All right.
The other thing too, by the way, is that the topology, the other critical thing for a charge pump is there has to be a charge capacitor balance, a charge balance. Like an inductor can't have a DC voltage and a capacitor can't have a DC current. So you have to make sure when you're switching the capacitor, you don't have a DC current. So for most of these topologies, it just inherently balances the charge in the capacitor. So for some of the multi-level buck stuff, we actually have charge balance circuits. So while it's running, we have to monitor the voltage across the cap to make sure that it's not drifting up or drifting down, and switch it, more or less depending, or pick the state depending on how it's operating. Anyway.
Okay, so lots of stuff going on, lots of magic going on behind the scenes. Yeah, awesome. All right, this one is, how many external components are needed to use the PE25304, and are the capacitors needed external, which I think
Yeah, I can answer. So we need one capacitor for the input side and two capacitor on the output side, just for the stability.
Okay. So very similar to just pretty much any standard IC. You got to put some power supply filtering out there and signal. Yeah.
Correct.
Okay. Okay. This question. Well.
So maybe I can mention a little bit about this. So this is conversion efficiency when it decreases, or what impacts the charge pumping.
Yeah.
So it's a majority of the losses in our charge pump are just the conduction losses of the MOSFET. So so if you run at a lower current, generally, there's an efficiency plot, and the reason it's dropping off at efficiency at higher currents. In a buck regulator, you can say, it's dropping off efficiency at higher currents because of conduction losses and also because of switching losses. In ours, we don't have the switching losses. They're not a big problem. And the charge redistribution losses are not a big problem. The conduction losses really dominate the power loss. So so you see the output volt, you see the efficiency droop as you go to higher current because you have an I²R loss to the conduction. So that's really what dominates it. And so that's what causes the efficiency to decrease at higher currents.
Got it.
I hope that answers it.
Yeah. Okay. I think it's helpful anyway. Yeah. This one, Kevin says, thanks you for the excellent presentation. I'm going to go to the question part at the end. Could you share the main technical challenges for this application, particularly in terms of transient response and power delivery?
So generally, most of the stuff that Kubo showed today is open loop, so it's not regulated. So he showed like a DC transformer. Basically, it's kind of like a transformer where it takes the input voltage and gives some ratio. You can either step up or step down. So have the output voltage is 2x or 3x or 4x the input, or 1/3 or 1/2 or 1/4 or whatever ratio you want. So generally, they're not regulated, and so often what happens is after the charge pump, they'll have a point of load converter. So now the input voltage to the point of load converter is much lower. So the point of load converter, the buck converter downstream that's going directly to the load, is really well regulated. Because it has a smaller input voltage, often it can react much quicker to the load, have a much faster bandwidth. Also, because it has a smaller input, it can have a smaller inductor as well, smaller physical size and other things. So low transient, I would say, would be kind of maybe similar if you had a DC transformer where the input would droop and come back, but it's not regulated. So that's what I would say. That's what I would say. By the way, if you're doing divide by n, so if the output voltage is half or a third, if there's ripple on the input, then the ripple on the output will be half or a third of what you'd expect to see. But they're just capacitors, so it's just kind of the transient of a capacitor, I would say. So some of the technical challenges, maybe I'll phrase this differently. I'm not sure about the technical challenges thing, but I'll say it like this. There are certain applications we fit in really well, and we do much better than a buck. And there's applications where a buck will do much better, I'll say. One thing, like Kubo mentioned, is our inductors always want to be cubes. So that's difficult if you want a low height application. So we can be, 1 millimeter height application. So there's some applications where people needed really low height. So they used our solution to achieve a really low height, if that was really important for mobile devices or something where they needed 1 millimeter height. Or sometimes if you want to do it on the back of a PCB, where you don't have as much height. The top of a PCB, if you're in a data center or something, you have lots of room in the Z direction. I always say there's always room in the Z direction. But in the back of the board, if you run out of space in the top, you can put it on the back. And it's very low height because there's no tall inductor. So that's one application. Another application is generally we do very good conversion from high.
Are we losing Doug there?
High efficiency from high voltage
Doug,
to a low voltage.
Hey, Doug. Looks like we're having some technical difficulties for you. Maybe try turning off your video. if you can hear me. Well, everything was going great there, and I'm not sure if Doug is frozen now. So yeah, we're all used to these technical difficulties, but we'll see if he comes back. Kubo, I think you can answer this one. Are the PE 25304 and 25208 available in automotive grades?
The answer is no. At the moment, so we have no plan to develop automotive grade part. We still keep investigating this market to see, if any play we can with our charge pump technology. Maybe in the future we may consider if ROI model makes sense to proceed. But the answer at the moment is no, unfortunately. Yeah, only for consumer.
Yeah. Doug, are you back for us? Nope, looks like he's gone. Okay, so technically. Well, let's see if we can get through the questions. If we can't get to them, Kubo, if you can't answer them, that's okay. We'll just archive them and reach out to people as need be. And of course, at any point, reach out to the pSemi team. They'd be happy to talk to you and follow up after that. So this question, what is the switching frequency for the 25304 and the PE 25208?
Yeah, I can answer. So the P25304, this is a module solution. The frequency is fixed at 270 kilohertz. On the other hand, the P25208, this is a discrete solution, and default frequency setting is 300 kilohertz. And there is a frequency pin allowing user to change between 270 kilo to 500 kilo by external register.
Okay, excellent. Thank you. Doug, welcome back.
Sorry.
Yeah, no worries. A couple more questions in the queue. Is there any limitation on the number of parallel units?
Basically, no. Technically, there is no limitation. So you can put any number of units in parallel. But however, of course, more units in parallel grow solution size and cost. So this is just, the matter of the balancing between performance and cost as per the application.
Okay. And then can the charge pump start up with a load?
So usually not. Usually you want very light load, because when we start up, we actually have to charge up the fly capacitors so that we don't overstress the MOSFETs. So there's a startup procedure. So the output voltage comes up, like a normal bucket, kind of comes up slowly. But generally, you don't want to load the output while it's starting up.
Okay, great. Well, excellent presentation, guys. Looks like we got through all of our questions. Any last thoughts you want to add to the audience before we close up for the day?
I just want to say thank you for joining today's webinar again. And we look forward to future business with you. And let's change whole power industry with this charge pump.
Sounds great. Thanks, Kubo. And thank you, Doug. Great presentation again, and really great discussion. And thanks to the audience. We had love seeing all those questions. In just a moment, you'll be redirected to pSemi's author page on All About Circuits, and you will be able to watch this session on demand. Just use the same link you used to join the webinar today. Thank you again, everyone, for participating. We look forward to seeing you at another live session hosted by ETech and All About Circuits very soon. Thank you.